So acids and bases are something that we encounter in our everyday life. They are things like orange juice, vinegar, baking soda, ammonia, soaps to some extent. So how can we classify anything as a strong acid or a base, or what makes something an acid or a base? So acids are substances that ionize in water to form aqueous protons. And so they're often called a proton donor, which means they give up, or it means they ionize into acid molecule, which is negative, plus an H plus. So in this case, a proton is an H plus. This is what we call a proton. And so they will give off this, which is considered an acidic proton. So here are two examples: vinegar, which is dilute acetic acid, and lemon juice, which is citric acid. And so if we think about an acidic proton, there are these things called polyprotic, which means they have more than one acid proton. So an example of that would be sulfuric acid, which up here has two acidic protons. So acids are always written, or often written, with the H's in front, which are acidic. Occasionally you'll see them at the end. So in this case, sulfuric acid completely ionizes into H plus. It's aqueous, so if this is an aqueous solution, plus HSO4 minus, also aqueous. And then the second polyprotic acid can come off in a second reaction. These are both aqueous. And so in this case, this is a complete ionization. This is in what's called equilibrium. Meaning in any given solution you have all three present, where in this case this direction means you've only got one. And so not all protons are acidic protons. So in some cases we'll have R, which is just any group. And then if we have a carboxylic acid, which is just an acidic group, this is going to be an acidic proton. But if we were to have CH4, which is methane, none of these are acidic protons. So acidic protons are only found in acidic groups. So the next thing we're going to talk about are bases. Bases accept a proton, but they produce an OH minus, or a hydroxide ion. And so we have ammonia, which is NH4 plus, and baking soda. And so these are bases that we tend to see every day. Now ammonia is a little different because it doesn't have the classic NH or the OH hydroxide group, whereas many of the others do. So ammonia is NH3, in this case it's aqueous, plus liquid water. And it's going to be in equilibrium with an OH minus, also still aqueous, plus NH4 plus, which is aqueous. And so in this case, the base, this accepts the proton from water, generating the hydroxide group. And so in general, we can identify the base by, for sodium hydroxide or potassium hydroxide, the presence of the OH groups are often what indicate that there's a base. So acids and bases come in different flavors, and so strong acids and bases completely ionize, where a weak acid and base partially ionizes. So the equilibrium arrows look like this, and the strong acids and bases will have one direction arrows. And so we can tell the difference if we look at them in an equation based on which of these arrows are present. Whoops. Okay. So strong acids and bases, these are going to become strong, they are strong acids and bases, and so they completely ionize. So all of these will separate into their ions, whether it's H plus and Cl minus, or HClO4, which is the H plus and the ClO4. All of these are strong acids. You'll note with sulfuric acid, it is only the first proton that is a strong acid. For strong bases, all of the group 1A metal hydroxides. So if we were to look at a periodic table, we are talking about group 1A, which is these group right here, minus hydrogen, and some of the group B, or the heavy group 2A metal hydroxides, such as barium, strontium, calcium. The other two, not quite as much. Please note you need to memorize all of these strong acids and bases to know what they are for different equations. So if you are not a strong acid or a strong base, then it turns out that you are a weak acid or base. And so in this case, these are going to not completely ionize. These will be in equilibrium. And one way to consider this is if they are not a strong acid or base, they are a weak acid. Acid or base. This is provided that they do have an acidic proton of some variety or a proton acceptor. And so in this case, we are going to classify them either as definitely a strong or a weak. And so in that case, we'll look at both of those. And so a non-electrolyte, right, if we remember from earlier sections, non-electrolytes are things that do not ionize. And so in this case, we are looking at complete ionization. So these will be complete. These will be partial. And these will not ionize. And so we know that things that are ionic bonds completely ionize. Some molecular compounds fall in either one of these. And so we're going to look at all three of these to see which of these are strong, weak, or non-electrolytes. Okay, so calcium chloride. This is an ionic compound, so this will be strong. This here is ethanol, so it's C2H5OH. Now, OHs often look like hydroxide groups, or it could also look like an acidic proton, so we need to take into account the environment. So in this case, ethanol is a non-electrolyte. Okay, so a non-electrolyte, there's no ionization. So the next one here is formic acid, and so this isn't on our list, but we know that this is not a strong acid. So therefore, it must be a weak acid. Okay, and so potassium hydroxide is on our strong acid list, so we know that this is a strong electrolyte. And so these two will completely dissociate. This one will dissociate partially. This will not dissociate at all. So when we mix acids and bases together, we are going to neutralize one or the other. And so in most cases, we will neutralize both. And so if we mix acid plus base, we will get out a salt plus water. In this case, you'll make liquid water, which is very different than aqueous solutions. And so in this case, if we were to look at sodium hydroxide and hydrochloric acid, so we have sodium hydroxide, both of these are going to be in aqueous solutions. When we mix those together, it's a metathesis reaction to some degree. This is a different type of metathesis. So the sodium and the chloride are going to come together. They will be aqueous in solution. And the other thing that we will get is HOH if we were to just combine these two, which is also known as H2O. These will be liquid. And so you can see that when we mix an acid and a base, we will get a salt and water. And so if we were to think about writing these out as half reactions or as complete ionic reactions, so in this case, we're going to write, this is our molecular equation. The complete ionic equation is sodium plus, which is an aqueous solution, plus OH minus, still aqueous, plus H plus, aqueous, plus Cl minus, still aqueous. Now, this is a strong electrolyte, and therefore we know it's going to completely ionize. So we have Na plus, aqueous, plus Cl minus, also aqueous. And then it turns out because this is liquid, it is not going to ionize. So we have H2O liquid. From the complete ionic, we can write the net ionic by removing our spectator ions. These are things that are present on both sides. We will get the acid-base half reaction, which is H plus aqueous plus OH minus aqueous goes to H2O liquid. Essentially, all of our half reactions are going to look like this for acids and bases. Occasionally, you will create more water molecules. So what about the neutralization reaction and the net ionic equation for magnesium hydroxide and hydrochloric acid? So magnesium hydroxide, if we use our periodic table, we see that magnesium is going to have a 2+ charge, and we know from the common ion table that hydroxide is an OH minus. So we'll have MgOH2, and hydrochloric acid is HCl. So when we add these together, we have magnesium hydroxide, which is aqueous, plus HCl. Now we know that we're going to get out water, which will be a liquid, and we know that we're going to get some version of magnesium and chlorine mixed together. So if we look at this, we know that magnesium has a 2+, chlorine has a 1-, so we know that it will be MgCl2. This will be aqueous. Now, we need to make sure our equation is balanced, otherwise it won't quite work. So for 2 chlorines, we're going to have 2 in front of the HCl. The magnesiums are balanced, but in this case, if we start to have 2 acidic protons, we are going to end up with 2 water molecules. So in this case, we can write the complete ionic equation, which is magnesium 2+, aqueous, plus 2 OH minus, aqueous, plus 2H plus, aqueous, plus 2 Cl minus, still aqueous. Now the waters, because they are liquid, do not come out of solution. And then we have magnesium 2+, aqueous, plus 2 Cl minus, aqueous. So we've now created our complete ionic equation. We can now rewrite the net ionic, which is 2 OH minus, aqueous, plus 2H plus, aqueous, goes to 2 H2O, liquid. Now in this case, because this corresponds to the balanced chemical equation, you can leave it as 2, 2, 2. You can also reduce this by 1. Either one is acceptable. So another example, the neutralization reaction. In this case, we're just going to write the neutralization, but you can write the net ionic on your own. So acetic acid is the acetate ion plus an H plus, and barium hydroxide. Barium hydroxide is Ba2, it's barium with 2 hydroxides. And so the balanced chemical equation is the acetic acid, aqueous, plus barium hydroxide, still aqueous. We are going to create barium acetate, which is going to be Ba plus the acetate group. But there need to be 2 of those because it's only a -1. Aqueous plus 2 H2O, which will be liquid. And so in that case, we'll need 2 acetate ions, okay? Now the net ionic for an acid-base neutralization is always the same. So we know that it's going to end up being 2H plus, aqueous, plus 2 OH minus, aqueous, and that's going to form 2 H2O, liquid. So the net ionics for an acid base are always going to be the same. Occasionally, instead of creating an acid-base neutralization where you form water, we will get one with carbonate ions, and those will release gases. And so during the neutralization reaction. So if we were to have 2 HCl aqueous, plus sodium sulfide, you would get H2S, which is a gas, plus 2 NaCl, which is aqueous. In this case, your net ionic would be very similar. It would have the acidic protons with the sulfide to create H2S gas. So if we were to use a carbonate, so the carbonate is CO3, 2-. So if we think about HCl, which is aqueous, plus sodium carbonate, also aqueous, we're going to get out our sodium chloride, which is aqueous. In this case, we're going to get carbonic acid, which is H2CO3, which is aqueous. This molecule right here is very unstable. Okay, once this is created, to some extent, it immediately begins to dissociate. So we have H2CO3 that's aqueous. We're going to unidirectionally pass into liquid water plus CO2 gas. This is going to come off, and therefore this reaction, when you mix it together, there is no equilibrium. Another example is if we use, or you could also write your equation this way, HCl aqueous plus sodium carbonate. You will get NaCl aqueous plus H2O liquid plus CO2 gas. In this case, once we form this molecule, it immediately dissolves into these, and so you can bypass this step when you write these reactions. So in this case, it would be H plus HCO3 minus. These are all aqueous. And then you would get liquid water out plus carbon dioxide gas. And so you can get different gases here depending on what your starting material is. But in a neutralization reaction with a gas molecule, don't forget that gases and liquids do not ionize in water.